This set of notes covers Chapter 7, Arrays, Part 1A, on Sections 1 and 2, Array Elements, and Declaring and Using Arrays. The array is the second data structure that we will be studying. The first was the class, which we use to define the blueprint of like objects. Interestingly, in Computer Science 121, you already learned everything about coding that is required to solve any programming problem. This has been proven mathematically by two gentlemen named Boehm and Chacopini. Now, before you run over to withdraw from the rest of the course, let me explain. You could theoretically formulate a programming solution for any programming problem, but I'm pretty sure it would not be easy to do or elegantly designed and coded. To solve large, complex problems, we need good data structures and good software development processes. That is our focus this semester. So let's continue with Chapter 7 on arrays. The topics we will be studying in Sections 7.1 and 7.2 include the following list. The topics covered in this presentation, labeled Chapter 7, Part 1A, include properties of the array data structure, array elements, and array declaration and use. Part 1B will cover bounds checking through arrays as parameters. There is a lot of meat in this chapter. You will need to study and review it in small units a few times in order to glean and master all of the material. It is well worth your time. Chapter 5 and this Chapter 7 are the two foundational chapters to the course and to your becoming successful programmers. The array data structure is a collection of indexed like items that is stored sequentially in memory. Let's take this definition apart. Here are the four important aspects of the array data structure, highlighted by the key concepts in the definition. First, it must be a collection. An array size of 0 is not allowed, and an array size of 1 is just silly, as it is no different from a singular variable or object. The importance of the collection stems from the convenience of recognizing the array as a group, and that we can process every element in common ways. Important characteristic number 2 is that each member is alike, or in programming parlance, of the same type or class. As with item 1, this provides us with the ability to have a common set of operations that can conveniently process every element of the array, because they are alike in their underlying structure. Number 3 specifies that they are ordered, which means we line them up and give each one a number or index based on their position in the line. Think of a list of items. Or another real-world example is a to-do list. And number 4 is important to the hardware because arrays are always arranged one after the other in memory. Because of this, they can be processed very quickly by the system. Other than class objects, the array is most important, versatile, and widely used data structure. We will examine arrays of primitive variables, arrays of objects, and objects that contain arrays. The entire array has a single name. Each value has a numeric index. Since the array is an ordered list of elements, we just use one common group name to identify it. Then we use the ordinal index numbers to uniquely identify each individual item. We also must define a size for the array. This specifies how many items are in the collection. Another important thing to always remember in Java, like C++, we always start counting from 0. So the first element in the array is array name sub-0. Notice that the first score, 79, then, is identified by the name score sub-0. And although there are 10 scores in the array, there is no scores sub-10. Commonly, the array size will be denoted by n, and always remember that the elements are therefore numbered from 0 to n-1 inside the array data structure. This makes them easy and efficient to process as they are stored sequentially in memory as a unit. An array is a group of unique elements. Each individual value in an array is identified by using the array name followed by its index in brackets. For example, the identifier scores sub-2 refers to the value 94, the third value in the array. This identifier, scores sub-2, represents a place to store a single integer and can be used in code wherever an integer variable can be used. The power of the array comes from its simplicity. The two primary ways we will want to process array elements will be to take advantage of their likeness, in other words, be able to quickly and easily treat them all the same way, one after the other, but we also want to be able to use and process any one individual element of the array apart from the group. And we can do both easily with arrays. Think about a programming problem where we would be asked to manage a company's payroll. Every week, we need to calculate the pay for every worker and then issue their paychecks. It doesn't matter if you are the CEO or a mail clerk. Every week, we are going to calculate your pay and then issue you your paycheck. Here, arrays shine because we can, one after the other, without a lot of coding, calculate each employee's pay and then issue their paycheck using a loop. Yet, if we need to individually give employee number 4 a merit raise for being employee of the month, we can individually select employee sub 4 and give her a raise. Let's review. The values held in an array are called array elements. Each element is uniquely identified by its integer index. An array stores multiple values of the same type, the element type. The element type can be a primitive type or an object reference. Therefore, we can create an array of integers, an array of characters, an array of string objects, an array of coin objects. In Java, the array itself is an object that must be instantiated, and this is in addition to instantiating the individual objects of the array. So let's examine how we declare arrays when programming. The first array we considered was the scores array. In the example here, we see the int group declaration formed by the type and an empty set of brackets. These brackets tell us and the compiler that this is a collection of ints, which we call an int array. This is followed by the identifier scores, our name for this array. We then initialize the scores array to hold 10 int elements by using the new operator followed by the type of element with the size of the array inside the brackets. This will allocate sequential memory space large enough to hold 10 integer values, 40 bytes of space. So the type of the variable scores is int brackets, which indicates an array of integers. Note that the array type does not specify how many. Its size is always defined on the right after the new. The reference variable scores is set to a new array object that can hold 10 integers. Here are a few more array declaration examples. Note the two styles. Number 1 shows the declaration with the new initializer set to size the array and allocate space, all in one line. Number 2 uses a two-step process. On the first line, we see the declaration of the Boolean array, and on the second line, we see the initialization of its size and space in memory. Regardless of the one-line or two-line style chosen, we consistently must identify the group type using the type name with a set of brackets and an identifier name for the array. And on the right side of the assignment, use the new operator with the group type containing its size. By default, Java will initialize the floats to 0 and the booleans to false. What do you suppose the char default is? How about int? Notice that the last example declares an array of coin objects called pocketful. This instantiates an array of 12 object references. Each of the coins will still need to be individually instantiated, as we will see later. As mentioned earlier, the two important ways we will want to be able to use our arrays in code are number 1 as a group, accessing them sequentially, and number 2, accessing them randomly or individually. Let's examine the as a group processing first. The first code example demonstrates the use of the for loop with the array of coin objects named pocketful. With an array, we don't need to repeat 12 lines of coin flip code in order to flip our pocketful of coins. Instead, we use the for loop and have the incrementer I range from 0 to size -1, which in this case is 11. Repeating 12 lines of code might not be too bad with cut and paste, but imagine the lines of code saved if we had 200 coins or 1,200 coins. The only change to this code would be our terminating condition. Do you see how the use of the array data structure can simplify our code? Good. Okay. Now let's look at the newer loop construct that you learned about in Chapter 4, the for each iterator loop. With this style, you create a class object that matches the array type and use it to flip all the coins in the array. Here we see each coin declared as type coin and that it will iterate over the collection pocketful. If you are processing the entire array of objects, these can be used interchangeably. However, if you want to go from last to first, or only process a range of the elements, you cannot use the for each. You would have to code the for loop to do either of those types of processes. Now let's take a look at accessing individual elements within the array. There will be times when we want to individually use an element of an array, and this is easy to do, provided you know the element's index. An array element can be assigned a value, printed, or used in a calculation if it is a numeric type. Let's review a few examples. In the first example, we change scores sub 2's value to be 89. In the second example, after declaring and defining integer variable first and setting it to 0, we add 2 to the value of scores sub 0. A Java rule that we have to follow is that our indexes have to be an int type. These first two examples change the values of the stored elements. We know this because they were on the left-hand side of the assignment operator. The last two examples just use the stored values of the elements without changing them. In example 3, we use scores sub 0 and scores sub 1 to compute a mean, and in the last example, we string concatenate the value stored in scores sub 5 to the output string top equals. And so we see that anywhere in code that we could use an integer, we could substitute a scores sub index element, as each element in scores is just an integer. Let's now look at a sample program from your textbook. This is a very simple program that uses an int array. It demonstrates basic array declaration and use. We will create an array, fill it with various integer values, modify one particular value, and then print the values out. So we'll see the sequential access of all the elements, and then the individual or random access of one particular element. First, we declare a constant using the reserved word final. That will become the size or n value for our array. This is a good programming technique. If for some reason the size of the array needs to be changed, we only need to change the constant value at the top of the program, so long as we use the constant throughout the code. Notice how we use it in this program. We also have declared a constant named multiple and set it to 10. Next, we declare an int array and name it list. We initialize its size to 15 by using the constant limit. Again, the author is demonstrating a standard practice programming technique that is used with arrays. This is followed by setting all of the list values to their index number times 10, the constant multiple. Again, notice the use of the constant limit for controlling the loop iterator. This program is cleanly coded and easy to change if the size of the array needs to be changed for any reason. The next line of code demonstrates the individual random access of one particular element by its index. In this case, the sixth element, named list sub 5. We change its stored value to 999. The last thing we do in the program is use the for each loop to display each value in the array. Note the use of an int iterator named value, the colon, and the name of the collection in this example, the int array named list. The value will iterate through one after the other from index 0 through 14, which is the size minus 1. Now look at the output. Is it what you expected? Notice that item number 6 was changed to 999. Do you recall the line of code that changed its value? Good. Shown here is a revised picture of the visual aid of how the basic array example program works. First, note that after we construct the array, Java will automatically fill the 15 integers with 0. This is different from C++, which does not do any automatic initialization for us. So before we start the first loop, each element of the array list will have a value of 0. The second column shows the array after the first 3 iterations of the first for loop. At this snapshot in time, we see that we have processed the first 3 elements by multiplying the index of the for loop times the multiple 10, and assigning that value to the element stored at its list subindex. The third column is a snapshot of the memory after finishing the first loop. Then we assign 999 to the sixth element, whose index is 5. So the last column shows us the contents of the array before we begin the second loop, the for each, which will print out all 15 of the list array elements in order from list sub 0 through list sub 14. This concludes Chapter 7, Part 1A on Sections 7.1 and 7.2 in your textbook. Happy coding!